2. And I told you that I was going to skip section 7.3 because the only thing that it talked about that wasn't already talked about was the central limit theorem. And I did that for you last time. All right? So we're going to skip section 7.3. So if you're looking at your syllabus, that means we are, as of today, back where the syllabus says we should be. All right? So we're right on track. So exam dates and all that stuff should match up. Okay? As just a quick review, what the heck does the central limit theorem say? That's how I will abbreviate it from here on out. Instead of writing out central limit theorem, I'll just say the CLT. What does the CLT tell us? Okay, that's part of it. But just in general, it has to do with sampling distributions, right? So what does it tell us about the sampling distribution? They're approximately normal. That's really the heart of the central limit theorem. It also gives us details about that normal distribution, which we'll put in. But the central limit theorem says the sampling distribution of a summary statistic and I'm going to put in parentheses x bar or p hat because those are the only two that we'll talk about. The central limit theorem applies to a lot of different summary statistics, but these are the only two that in this class we'll worry about their sampling distribution. Okay? So the sampling distribution of a sample statistic like x bar or p hat will be approximately normal I'm going to put in parentheses for a sufficiently large sample and remember that discussion about when can you assume that the normal approximation is a good one? Well, as long as your sample's big enough. Okay? So do you remember how big the sample had to be for proportions?
At least 30?
That was for means.
Oh.
At least 30. It's sort of related to that for proportions. But it had n times p greater than or equal to 15 and n times 1 minus p greater than or equal to 15. Which in English, that says at least 15 successes and at least 15 failures. Right? So if you add successes and failures together, that's saying you got to have at least 30 in your sample size, but it has to get quite a bit bigger than 30 if your p gets very far away from 0.5. So if you're up near 1 or down near 0, you might have to have 1,000 in your sample in order to get 15 successes. If you're looking at estimating the proportion of some really rare event, in order to get 15 of those events, you need a big sample. Right? So that's sufficiently large sample. N equal 30 for means, and then at least 15 successes and 15 failures if we're doing proportions. Okay? So then, once we know the distribution is approximately normal, it's bell-shaped and symmetric, where is it centered? So I'm going to say with mean, and it's different for x bar and p hat, so I'll do the two cases. Mu of x bar is equal to what? If we're doing means, the mean of x. So mu x, so this is the population mean. If we're doing p hats, what's the mean of p hats? In other words, where will that distribution be centered?
P.
P. Now it's interesting, you need to understand that p hat is an estimate of p. So this is saying that the sampling distribution for p hat is centered at the right place. It's centered where you would hope it would be centered. same thing for means. X bar is trying to estimate mu sub x. So it's centered at the right place. It's centered at the thing you're trying to estimate. Okay. And the last thing, and standard error, if it's a means problem, the standard error of x bar is equal to what? I see everybody frantically writing, trying to get all this down. It should already be in your notes from last time. This is review, right?
Population.
Okay, population,
Standard deviation.
which a symbol is lowercase sigma
Over square root of n.
over square root of n. And that's for means. So I forgot to write proportion here. So with mean, oh wait, I'm sorry, I don't need that there. So this is for population mean, this one I forgot to write, population proportion. And then here is for means, if it's proportions, standard error of p hat is
Square root of p times 1 minus p over n.
over n, just like that, okay? So sample standard deviation divided by square root of sample size. If it's a mean, if it's a proportion, then it's the square root of p times 1 minus p all over n. Okay? Now, homework tonight is section 7.2. I had hoped in class last time to do 2 example problems, but I didn't have time to do that. So the second one, how many people have already completed that homework set? Looks like 4 or 5 of you out of all of you. So it's probably worth talking about a little bit. One of the homework problems mimics problem number 720 in section 7.2 in the book, page 332. So go to page 332 if you have your book. And this is the one about Jan's all-you-can-eat restaurant. Right? I like all-you-can-eat restaurants. Right? Only nowadays, I'm old and I don't eat a whole lot. College kids can eat a ton. Right? So think about if you ran an all-you-can-eat restaurant and you see the Washburn football team walk in. What are you thinking? Oh, crap. Right? That's what you're thinking. Because you're going to lose money on those guys. Right? But when you see, this name popped into my head, Ruth Circle, that's like an old woman's group at a Methodist church. That's the one at our church. Anyway, if they walk in, you're thinking, cool. Right? They don't eat a whole lot. Right? So in order to make a profit, Jan charges $8.95 per meal, right? So that's the price of the meal. From past data, she knows that the mean expense is $8.20. So on average, people eat $8.20 worth of food. Well, if she's charging $8.95, she's making a profit, right? But wait a minute, she's not making a profit on everybody. If a football team comes in, she's not going to make a profit on them. What she's saying is, on average, she makes a profit. The standard deviation is $3. So some people come in and they eat $8.20 worth of food. Some people come in and they eat $11.20 worth of food, and they're only 1 standard deviation above the mean. Some people go down to $5.20, they're 1 standard deviation below the mean. Right? So in order to make a profit, does everybody on a given day have to be above the mean? I mean, let me start that over. Does everybody have to be below $8.95? No. What has to happen? Let's suppose 100 people, and that's the scenario here. 100 people came in to eat. What has to be true in order to make a profit on the day? You don't have to make a profit on every single one of those 100 people. The mean has to be less than $8.95. So in order to make a profit, and this is the way it's worded, find the probability that the restaurant makes a profit that day with a sample mean expense being less than, what would your sample mean need to be less than? $8.95, right? So find the probability that the sample mean, which we call X bar, is less than $8.95. Now how do I compute that probability? Give you a hint. Yeah, it's with the calculator. What does the central limit theorem tell us the distribution of X bar will be? Normal. As long as the sample size is at least 30. Is it? Yeah. They said 100 people came in. So we got a sample of size 100. Right? So all you need to do is compute the standard error of X bar. And the standard error of X bar will be what? Central limit theorem again. Standard error of X bar is sigma over the square root of n. So that's 3 over the square root of 100. I'll do that in my head. It's nice of them to give us numbers that were easy to do, right? Square root of 100 is 10. 3 divided by 10 is 0.3. And that's in dollars, so that means 30 cents. So the standard error of X bar is 30 cents. Okay? Well, draw the sampling distribution. I always tell you, if you're doing a normal probability problem, the first step you should do is to draw the distribution. Since we're talking about a probability based on X bar, I need the distribution of X bar, not of X, but of X bar. X is individuals. That's that one football player guy. But what I want is the mean of 100 people. So that's going to be centered where? Where's the center of this sampling distribution? Right? That's what this says. The center of the sampling distribution is the population mean. What's the population mean? 820. Halfway down the hill should take me out to where? 1120? Some of you are nodding. No. What is this, the distribution? See, I faked you into nodding by nodding myself. What is this the distribution of? X bar or X?
X bar.
X bar. Is this the variability in X bar? No, this is. Right? So halfway down the hill should be that far, 30 cents from 820. So that's at 850. Go one more standard error, and where are we out to?
790.
880. Somebody said 790, and you're going back the other way, which I probably should do. So down here would be 790, like that. Okay? Well, where is 895?
Above.
It's another half of a standard deviation, right? Because it's 15 cents beyond 880. So it's, if I went to 3, it would be out there. So 895 is right there. Now, for this probability, where do I shade? Everything less than that. Since I know it's a normal distribution because of the central limit theorem, and I know the mean, and I know the standard error because of the central limit theorem, I can compute this probability using, on my calculator, which function? Normal CDF. Okay, so do that real quick. Plug this into your calculator and get the answer. And then I will, I don't have my calculator, so I start to say I will compute it, tell you if you got it right. But I will rely on you guys. We'll get a consensus and see what we have.
You have to put 0.
Where does, remember normal CDF, you enter 4 things. Left edge of the shaded region, right edge of the shaded region. Then the mean, than the standard deviation, only now it's x bar, so we put the standard error, right? So where is the left edge? Is it 0?
Infinity.
Put negative infinity. Technically it is 0 because you can't go less than 0 for an expense, right? And you'll get the same answer. If you put in 0, you'll be okay, but I always tell people, put in negative infinity or infinity. Just get in that habit, because sometimes you're not okay if you put 0 if negatives are possible. Don't get in the habit of using 0. But here, 0, not only is 0 the boundary, but it's a lot of standard errors from 820. So going there, that's to the calculator, that's pretty much infinity. The distribution has come down to basically nothing by then anyway. So anybody have the answer? You got it?
Yeah, it doesn't seem right. 0.994, I guess.
0.994? And why doesn't that seem right?
I don't know. It seems like she's always going to make a profit. I don't know. I mean, if the way
Almost
she
always
priced it
going to
makes
make a
sense,
profit. Now, if you were Jan, would you like that
then-
number?
Yeah.
Yeah. You're almost guaranteed to make a profit. If you look at the picture, it looks, that looks right. I've shaded almost everything. Right? And that's and it is correct. And that's what you would want. If you're a business owner, you want a very high probability that you make a profit on any given day. Now, what's the most common mistake for this problem? Any guesses?
Using the 3.
Using the 3. So instead of what you just did was normal CDF from negative infinity to, I didn't leave enough room, to 895 with a mean of 820 and 0.3. So I'm going to get rid of this stuff just because I think we're done with it. Most common mistake is to put 3 in there. You don't put 3. If you do put 3, what are you computing the probability of?
The whole
Each person. You're computing the probability that the next person that walks in, you make a profit on that person. In other words, you've done a sample of size 1. But this is 0.3 is a sample of size 100. Okay? Everybody understand that? It's a little bit tricky of a problem because you know, the 895 and the 820 and expenses and all that stuff, things that we don't usually have to think about in statistics class. But this is how you apply this stuff. This is why the central limit theorem is so important. Without the central limit theorem, you would have no idea how to compute that probability. Okay, so carrying on with that theme, we're going to go to section 8.1, which takes us into the realm of statistical inference. And early in the semester, we defined what we meant by statistical inference. Do you remember that? What does it mean to infer something? What's that?
Draw a conclusion based on results.
Exactly. Draw a conclusion based on results from a sample. Right? And it's a conclusion about what? About the population. Right? So that's what we mean by statistical inference. We're making conclusions about the population based on what we saw happen in our sample. The sampling distribution of your summary statistic from your sample is key to making that inference. Okay? Now let's say that I ask you, you're my hired researcher, right? And I want to know what proportion of American college students support a concealed carry law. You know what that means? That, you know, you're allowed to carry a hidden handgun, right? Like you can have a gun in your purse. Right? Suppose I ask you to estimate that proportion. How would you do that?
Random sample?
Okay, you take a random sample of American college students, right? And then from that sample, what would you do? It's not a trick question. It is a very simple answer. You would compute from your sample.
Who carries and who doesn't?
What?
Who carries and who doesn't?
Okay, who carries and or who supports and who doesn't. Just because you don't happen to carry a gun doesn't necessarily mean that you don't support it. You might say, well, yeah, it's okay. I'm not going to do it, but it's okay. So you would compute from your sample the proportion of people who say yes to that question, right? And what do we call a proportion from a sample? It's a summary statistic, the sample proportion. What notation do we use? Look at your notes. P hat. We just had it up here, right? Compute P hat, the sample proportion. Okay? Now let me ask you this question. When I ask you to do this, you've had statistics. So you know how to draw a simple random sample. You know how to do things in a statistically valid way. So did you get it right? Your P hat that you compute, is it right? What do I mean by right? What are you trying to estimate?
Population.
The population proportion, which we denote as what? P. P with no hat on it, right? The hat means estimate of. So P hat is estimate of P, right? So we use that to estimate P. Now, you did a really dandy job at this research. Did you get it right? No. I can guarantee you, you will not get it exactly correct. Your proportion from your sample will never be exactly what the proportion is in the population. Yeah?
Could there be lurking variables like what part of the country you're doing it? Because I think the Southerners like to carry more than Northerners.
Okay, now let's not get biased about regions of the country, but yes, absolutely. There certainly would be lurking variables, and if you really did a valid survey, you'd want to kind of control for those kind of things and maybe take them into account when you make the assessment. But we're going to ignore all that for now, right? The point here is that no matter how good your sample is, you're never going to get it exactly right. We know that there's going to be some error in that estimate, right? P hat is called the point estimate of P. And the reason we call it a point estimate, think about drawing a number line. And on that number line contains all of the possible values you could get back for P hat. Now it's a proportion, so what's the smallest it could be? 0. What's the biggest it could be? 1. Okay? So let's say that we get from our sample, we get P hat equal to 0.4. 40% of the people in the sample said, yes, I support that law. Okay? I'm making up numbers. I have no idea if it'd be anywhere near 0.4. But so on the number line, 0.4 is going to be right about there. It's called a point estimate because we literally can put a point on a number line and say, there's my estimate. Okay? But I know I didn't get it right. Right now we're 1 week away from the midterm elections, right? So there's all these political polls going on, trying to see who has a lead in one race or another, right? And when they quote a percent from their survey, what do they usually include with that? A margin of error, right? So they'll say, you know, we estimate that Sam Brownback is going to get, actually I don't remember what the latest poll was, but he was ahead, so we'll say 55%. He's going to get 55% of the vote, and that has a margin of error of plus or minus 3%. Okay? When they say a margin of error, they're putting an interval around that number. So on a number line, if I put an interval, I call it an interval estimate. So we have a point estimate, which is a single point, and we have an interval estimate, which is an interval of values. Okay? A confidence interval is an interval estimate. Let me just write it down here, I guess. And the way the book writes it, I like this. He says, an interval of values that contain the true proportion, or it could be means or whatever, but the true value in the population I'm sorry, the true proportion, let me add to this, that contain values that are most believable. For the true proportion. Okay? Now let me read that. A confidence interval is an interval of values that contain values that are the most believable, I left out the word the, are the most believable values for the true proportion in the population. Okay? So if I do my sample, and I do a really good sample, and it's a big sample, and I have, I'm very confident about the accuracy of my sample, I might look at my point estimate of 0.4 and say, well, I know it's probably not exactly 0.4, but I'm very certain that it isn't 0.8. So 0.8 would not go into my interval. It's not plausible. It's not believable. So what values would be believable? Well, the way that the interval is formed, first of all, we give it a confidence level. The most common, by far, confidence level is 95%. So we say we are 95% confident. So CI is my abbreviation for confidence interval. So a 95% confidence interval is the point estimate plus and minus the margin of error. And remember, I abbreviate margin of error as MOE. Right? So margin of error. And that's all there is to confidence intervals. So when they say Sam Brownback has 55% of the vote with a margin of error of plus or minus 3, then what's the confidence interval? Well, the point estimate would be 55%. The margin of error is 3. So 55 minus 3 is 52 up to 58. So the confidence interval would be 52 to 58%. Now, confidence intervals can be written as proportions or percents or whatever. So you just take your point estimate, add and subtract the margin of error, and you get a confidence interval. Where does the 95% come from? Well, it comes from how you compute that margin of error. By the central limit theorem, we know the distribution of our point estimate. We know that it follows a normal distribution, as long as I have a big enough sample. Whether it's p hats or x bars, I know by the central limit theorem that I got a nice normal distribution. Since I'm doing proportions, where is that going to be centered? P. Now I don't know what P is, because that's why I did the sampling. I'm trying to estimate P. But whatever P is, I know my sampling distribution is going to be centered at that P. Halfway down the hill will be what? P plus, what?
SD?
Not SD,
SE.
SE. P plus SE of P hat, which is the square root of P, 1 minus P all over N, that thing, right? And then halfway down the hill on the other side is P minus standard error of P hat, right? So how many standard errors do I need to go to get 95%? 2 standard errors. So this margin of error for 95% confidence, and we call that the confidence level. You go roughly 2 standard errors. Now I say roughly because we now have our normal CDF function in our calculator, and we can actually compute the probability of being within 2 standard errors, and it's a little higher than 95%. It's actually 0.9544. So if I want to do 95%, I give it a number slightly less than 2, and that number turns out to be 1.96. We won't formally do that until next section, 8.2, so we'll do that on Friday. But the point is, the margin of error, I should have written above this, margin of error equal, we'll do it like that, margin of error equal 2 standard errors for 95%. Now, if I said, well, I only want to be 90% confident, would that interval be wider or narrower than the 95%? Wider?
Narrower.
It is one or the other. And you said, trick question. And it kind of is a trick question. But think of it this way. This is the insight I want you to get into this. By definition, a confidence interval contains values that I am confident are believable for the true value, right? Or in other words, another way to say that is, I am 95% confident that the true value is in there. If I want to be more confident I got the true value, I need to put more numbers in there, right? So I got to make it wider. If I can be less confident, then I can take some numbers out, right? So I make it narrower. So in other words, if you do 90% confident, you don't need to go 2 standard errors. You need to go where? In. Less than that. So you want the area in here to be 90%. So 0.90, you can go in further. So in general, the margin of error is Z times the standard error. Where that Z, remember Z is a Z-score, number of standard errors. Right? So you tell me what confidence level you want, and I can tell you how many standard errors you need to go in order to get that confidence. So the margin of error actually depends on what confidence level. So when they quote it in the paper and they say plus or minus margin of error of 3%, what was their confidence level? We don't know. They never say. The media will never say margin of error is plus or minus 3% for 95% confidence. But I guarantee it is 95% confidence. That's just the standard practice is to compute 95% confidence intervals. So if it's not stated, assume it's 95%. Okay. So again, computing what that Z is, we'll do that in the next section. So for now, just all the problems that we'll do in this section, they'll just give us the margin of error. And then we form the confidence interval just by doing point estimate plus or minus that margin of error. Okay? So, suppose I'm back to my example with the concealed carry question, and I took a big enough sample that I get a margin of error of plus or minus 2%, or margin of error equal 0.02. Give me my confidence interval. Point what? 0.38, good. To 0.42. Okay. Now we can answer some questions. First thing I will always ask you to do is interpret that interval. What is that saying? What does that say? 0.38 what? 0.42 what?
Percent?
Okay, percent. What is it we're saying? Always start that sentence like this. We are 95% confident that. Now finish that sentence. What is it that we're confident of?
The value falls within that range.
Okay, the value. The value falls in that range. The value of what? I've erased it, but what were we trying to estimate in the beginning?
Proportion of people that support it.
The proportion of people who support the concealed carry law in the population. So that's P, right? So we are 95% confident that the true value of P, the true population proportion of people who support the law, is somewhere between 0.38 and 0.42, or 38% and 42%. That's how you interpret a confidence interval. Okay? Is it safe to assume that less than a majority of the population support this law? Yeah, because the confidence interval excludes what? What would a majority be? Numbers bigger than 0.5. And there are no numbers bigger than 0.5 that are plausible. The confidence interval contains all the plausible values, and 0.5 isn't in there. So we're saying it is not plausible that the true proportion is bigger than 0.5. Okay. So that's statistical inference. I don't know what the exact P is, but I know from my sample that it's not plausible the exact P is anything bigger than 0.42. Okay, so that's confidence interval. All right? Now, suppose you hire me as a statistical consultant to estimate a population proportion of something, and I base it on a sample of, say, 5 people. Right? I base my estimate on a sample of 5 people. What's my margin of error going to be like? Well, the standard error of p hat is square root of p times 1 minus p all over sample size, right? And let's say that in the population the true proportion is 0.4. So what's my standard error? Well, it's square root of 0.4 times 0.6 all over 5. I took a sample size 5. Right? Now, what is that number? What'd you say? Did you get it right?
Point
I didn't get it.
048.
Point,
0.219.
Oh, I forgot square root.
yeah, you square root that thing and you get 0.2 what?
19.
0.219. Now, if you're keeping up and you're understanding what you just computed, you should look at that number and go, God, that's terrible. If you're not keeping up and you have no idea what we just computed, you go, it's just a number. What does it mean? What is that number? That's the standard amount of error in my point estimate from a sample of size 5. So it's saying you can be off by 22% with no problem at all. What's my margin of error going to be? 95% confidence. 2 of those standard errors. So what's 2 of those? point 438. So what's my confidence interval? I didn't say what p hat was, but let's suppose that p hat from a sample of size 5, what are the only possible values for proportion that you could get? 0, 1 success out of 5 would be 0.2, 2 successes would be 0.4. So let's say I got exactly 0.4. I got 2 successes out of my 5. So I actually got it right. What would my confidence interval be? Well, it would be 0.4, my point estimate. Remember, point estimate plus or minus margin of error. My margin of error is 0.438. Negative 0.038 up to 0.838. Right? So you hired me as a statistical consultant to estimate this proportion for you, and I come back after months of hard labor. I come back and say, like all good statisticians, when you ask the question, what is the population proportion? I'm going to say, I don't know. But I'm 95% confident that the true value is somewhere in there. And then I'm going to give you my invoice for my consulting time. And what are you going to do? That's not useful, is it? You probably knew that before I ever did the study. That's somewhere in there, right? So how do I make that interval useful? I need to make it more, I need to narrow it down. How do I make the interval smaller? Sample bigger. N is on the bottom of a fraction. If you want to make the standard error smaller, you got to make N bigger. So you take bigger sample size, you decrease your standard error, which in turn decreases your margin of error and makes your confidence interval narrower. Right? So we won't do it for a little while, but only a few sections down the road. One of the most important contributions a statistician makes in a research project is to tell them how many people you need to look at. What should the sample size be in order to get an accurate estimate of the population proportion? And the statistician will ask the question, well, how accurate do you want to be? What kind of margin of error are you willing to live with? Once they tell you the margin of error they want, then you can figure out by just algebra what N needs to be. So if you don't learn anything else from this little example, learn that you never should try to estimate a proportion from a small sample. Did I talk the other day about the FDA meeting I was just in? Didn't I talk about that? And that was exactly the problem. They had samples in that, there were studies, published studies that had samples less than 5. 4 and 3 and 2, and they were estimating proportions from those. You expect wild variability. It could be anywhere in that interval. So. All right, so here we go. This is problem 8.6 on page 361 of the book. This is one of the online homework problems that you'll be doing. 8.6. And what it says is that the starting salaries of a random sample of 3 subjects who graduated from North Carolina State University with majors in mathematics had salaries of $45K, $35K, I'm too lazy to write the zeros. So $45,000, $35,000, and $55,000 a year. Okay? What's my N? 3. Sample of size 3. Part A says, find a point estimate of the population mean. Mariana, what'd you say? You were making lip movements? Okay, well then I'll just call it. Don't be afraid of being wrong. I like it when people are wrong because then that shows the most common mistakes. What's the point estimate of the population mean? No. She said p hat. This is not a proportions problem.
X bar.
This is a means problem.
Or X.
X bar. Right? And that's the thing I was expecting because we just did a bunch of stuff with proportions and then I jumped to this one on you. And that's kind of a dirty trick. But it would be p hat if it were a proportions problem. This is a means problem, so it's going to be X bar. So the point estimate is X bar. X bar is equal to what? You can do it in your head here. I want a number. What'd you say?
45.
45. And I'm going to go ahead and put the zeros this time. 45,000. Because notice these three numbers are evenly spaced, and 45 is the middle one. So by the way the means computed, that's going to be the value. Right? So that one we could actually do in our head. Right? Part B says, a method that we'll study in section 8.3 provides the margin of error for this point estimate. And the margin of error, they tell us, is $24,800 for 95% confidence. Construct the 95% confidence interval. So let's do it, and let's put it in interval notation. Hey, Tanner, tell me what to do to get this confidence interval. Yeah, you do. What does it say right here to do?
Plus or minus margin of error.
It says take the point estimate plus or minus margin of error. I've got both those things written right here. So what do? We take 45,000 and we subtract 24,800, and that gives me the lower bound. And then I add 24,800 and I get the upper bound. Right? So do those for me on your calculator real quick.
20,200.
20,200
69,800.
and then 69,800. There's the confidence interval. Okay? It doesn't ask you to do this, but interpret that interval for me.
95% confident that the salary is between 20,200 and 69,800.
Very good. Well, I'll say it louder. She said, we are 95% confident that the true population mean, I'm adding a little bit to what you said, the true population salary, mean salary, is between 20,200 and 69,800. Now this is another example where that interval is not very useful, is it? It's too wide. You know, that doesn't narrow it down into a region that's useful. But anytime you base an estimate on a sample that small, you get really wide confidence intervals because the standard error is so big. But that's the point of Part C. Part C says this. Use this example to explain why a point estimate alone is usually insufficient for statistical inference. If all I told my readers was that, hey, I did this study and I found that the average starting salary for math majors at North Carolina State was $45,000 a year. Sounds pretty good. What does this tell you that just the point estimate does not?
It could be a lot lower than that.
It could be a lot lower than that. Or it could be a lot higher than that. You need to see the confidence interval to let you know how accurate this is. It gives you an idea of the precision of this estimate. This estimate is not very precise because it could be anywhere between those. If instead I had a confidence interval that went from 44,000 to 46,000, that's a very precise estimate. Right? I know within $1,000 what the true population mean is with 95% confidence. Okay. remember that being a statistician means never having to say you're sure. We say things like, well, I'm 95% confident that it's somewhere in this interval. All right, section 7.2 homework is due tonight by midnight. 8.1 will be due Friday by midnight, and we won't have a section 7.3 homework because I'm skipping that section. All right, we'll see you on Friday.